All right, so let's move on and solve systems of equations using matrices. This solving system of equations using matrices was also known as the Gauss-Jordan elimination method. Okay, I'll get to more of that in a second. But let's look at the definition of a matrix. A matrix is any rectangular array of numbers. So I've given you 3 examples here. Now here's something I need you to be very cautious about. When you are solving using matrices, you need to make sure you have these brackets around the matrices. Because if you put straight lines, it means something completely different. With me? Okay. Also, something I need you to understand is then when we use the Gauss-Jordan elimination method, okay, we're going to be using the elimination method. So, back to our matrices a moment. These matrices have a certain order, as it's called. And when we talk about the order of a matrix, we're talking about the size of a matrix. Cool? Okay, so if I'm talking about the size of a matrix, then it's kind of like a room where I am talking about the length and the width of a room. If we say the room is like a 10 by 12, then we know it's 10 long by 12 wide. Cool? Okay. When we talk about the order of a matrix, we're talking about rows by columns. Now, rows go which way? Good, rows go left and right. Columns go which way? They go up and down. Matrix A has 2 rows and 3 columns, correct? So the order or the size of this matrix would be known as a 2 by 3. 2 rows, 3 columns. Matrix B, remember, rows by columns. How many rows does matrix B have? Yeah, technically it has 3 rows and only 1 column. This is a 3 by 1. And last but not least, matrix C, yeah, that one's a 2 by 2. It's also known as a square matrix for obvious reasons. Cool? Okay, now let me get back to that elimination method for a moment. Remember the elimination method. If you were solving systems of equations that look something like this, we would need to choose one variable to eliminate and get the coefficients the same, right? So for instance, if I chose to eliminate the x's, I would multiply this top equation by a -2 so that this top x and this bottom x, when I add them together, would cancel out, wouldn't they? Well, that's basically what we're doing using matrices, using Gauss-Jordan elimination, but we're using them without variables, which actually makes it a little bit shorter to deal with. With me? So hang in there, stay tuned, I've got an example. Okay, so let's take a look at this first problem. They're asking us to solve this by using Gauss-Jordan elimination. Now, it's also known as solving by using row-reduced echelon form. That's how it's called nowadays, okay? But it used to be called Gauss-Jordan elimination. And I still like this title because this title tells me I'm actually using the elimination method. And since it is the elimination method, I need to make sure my equations are set up in the right format. The format is all my variables on one side of the equal to sign in alphabetical order, x, y, z, and everything that's not a variable on the other side of the equal to sign. So gratefully, these are set up correctly. Are you with me? Now, I'm supposed to set up a matrix using these 3 equations, but I'm setting it up without using variables. So here's the deal. What order do you think the matrix is going to be that we're going to set up? Well, if you said, well, it's going to have 3 rows, you're right, it's going to have 3 rows. 1 row for each equation. Now my question to you is how many columns? Some of you got it, which is why you need to make sure you set it up according to the elimination method. 1 column for x, 1 column for y, 1 column for z, and 1 column for those answers. Are you with me? So the matrix we're going to set up is a 3 by 4. 3 equations, 4 columns, 1 for each variable and 1 for the answer. So our setup or our matrix is going to look like, for the first row, -4, -9, -1, and I was always taught to put this dotted line in, and some authors of the book don't put it in. I still think it's very good to put it in because it tells me that's where the equal to sign should go. So it helps me delineate between the two. Got it? Now my second row is -8, -6, -2, and -14. And my last row is 6, 9, 1, and 19. This is why it's extremely important that the equations are set up correctly. Because now the matrix is going, well, my first column is all x's. So those all better be the coefficient of x. My second column is all y's. Third column is all z's. The numbers on the other side of this dotted line are all the answers. Good? Okay. So now Gauss-Jordan says when you're solving, first thing you need to do is identify what I like to call the main diagonal. Now diagonals go this way, don't they? So the main diagonal starts in the upper left corner and goes down. So when I look in the upper left corner and circle all the numbers down to the bottom, so to speak, these numbers are on my main diagonal. Gauss comes along and says after you've identified that, you're supposed to get zeros below the main diagonal. Well, Jordan comes along later and says if you're going to get zeros below, you might as well get zeros above also. So here's the deal. By using the elimination method, we're going to make everything, except for the main diagonal, equal to 0. Okay? Everything above and below the main diagonal is going to be 0. Whatever happens to these numbers happens to these numbers on the other side of that dotted line. I don't care what happens to them. They can do whatever they need to do. Cool? Okay. So math is very consistent. You work left to right, top to bottom. So when I'm coming in from the left, the first column I see are x's. So I'm going to eliminate my x's first. And I'm going to go from top to bottom. I'm going to eliminate the -8 first and the 6 second. Now, remember, we're using the elimination method. But Gauss-Jordan is a little bit specific in terms of which numbers you can use to make everything else go to 0. Let's look at those x's again. I'm eliminating these two. I'm not eliminating the -4. So here's the deal. In order to make the -8 into a 0, I'm going to use that -4. In order to make that 6 into a 0, I'm going to use that -4. Are you with me? If I'm trying to get something to be a 0, I'm going to use the number on the main diagonal to help me do it. And since these are x's, I can only use another x to help me get rid of x's, which is why that -4 is going to help me get rid of the -8 and the +6 because they're all x's. Good? Okay. Now think of the elimination method. The elimination method says these numbers need to be the same but opposite signs. So the first number I'm eliminating is -8. And I'm going to use that -4 to help me do it. They need to be the same number, like a common denominator, if you will. So they both can be turned into, good, an 8, which means that, and just watch how I write this, okay? That -4 needs to get multiplied by what? Yeah, it needs to get multiplied by a 2, but it needs to get multiplied by a -2, so it's the opposite sign, correct? So now here's the deal. Remember, this first row is an equation. Do you multiply just the one number by a -4, or do you multiply the entire equation by -4? Yeah, you multiply the entire equation by -4. So I'm going to take -2 and multiply it to the first row. And in the elimination method, you add it to the other equation, don't you? Well, I'm going to add it to the second row. With me? And the answer is going to go into which row? Yeah, it's going to go into row 2. Cool? Okay. So, let me get my matrix. Am I trying to get a 0 in the first row? No, I'm not. Which means the first row is not changing because I'm not getting a 0 in the first row. So the first row is not changing. Remember that. Am I trying to get a 0 in the second row? Yes, I am. And this is the work we said that we're going to have to do it. Right? Okay, so remember what we said. We're going to take row 1 and multiply by -2. So when you take the first row and you multiply by -2, we get +8, +18, +2, +38, don't we? And we're adding it to the second row, which would be -8, -6, -2, and -14. So when we add these are the numbers I get. Hopefully you agree. So this is my new second row. Cool? Okay, so just got rid of the -8, but I also have to get rid of the 6. So when I get rid of the 6, again, I have no choice. I have to use that -4. So I need the numbers to be the same. I need like a common denominator between a 4 and a 6. Yeah, 12. So to the first row, you're going to have to multiply by 3 and add it to, yeah, that third row, you're going to have to multiply by 2, aren't you? Because 3 times 4 is 12, 2 times 6 is 12. And your answer will go in, that's right, the third row. So when you're looking at doing this work, you're going to do 3 times the first row, which would give us -12, -27, -3, and -57. And you're going to do 2 times the third row, which would be 12, 18, 2, and 38. And when you add those together, we get 0 and -9. We get -1 and, yeah, -19. Correct? So this is my new third row. How's this doing? Making sense? It's the elimination method. Remember that. Okay, so notice, and I got rid of the negative, I got rid of that 6 now. So notice in this first matrix what we did. This first matrix, we eliminated the x's, didn't we? So from this matrix to the next one, what do you think you're going to do? Yeah, you're going to eliminate the y's. And to the next one, eliminate the z's. So hang in there. I'll be right back with us eliminating the y. Okay, so we just eliminated the x's, correct? And now we got to go to the y's. Agreed? Now, occasionally, and I say occasionally because clearly it doesn't happen all the time, occasionally there is a matrix in between eliminating one variable to the next. And that matrix is what I call a reducing matrix. I'm noticing that I can take the second row and reduce by 12, and it will make the number smaller and more manageable to deal with. Are you with me? So I'm going to do that. So again, I'm only reducing. That's what this matrix is doing. So I'm going to take that second row and I'm going to divide by 12. And all that's going to do is make the numbers more manageable to deal with. This is what I call just us reducing. This is a reducing matrix, shall I say. Okay, so we get 0, 1, 0, and 2 there. And everybody else is staying the same. So in this matrix, all I did was reduce. Cool? Okay, and then we start the process over. We need to identify the main diagonal, which is in the upper left corner. So in this case, it has -4, +1, and -1 on it. And my goal is still the same, to get all the numbers above and below that main diagonal to equal 0. Well, in the last matrix, we got rid of the x's. Now it's time to get rid of the y's. Now I need to get rid of this both of these -9's. But remember, the only number you're allowed to use to get rid of those -9's is the 1, because you're not trying to make the number on the main diagonal 0. You're not trying to do that, which means that's the number I'm going to use to get everybody else in that column to be a 0. With me? Okay, so let's take a look. Remember, it's still the elimination method, which means I need this -9 and this 1 to be the exact same number, but opposite signs. So what do you think you're going to have to do? Yeah, you're going to have to multiply that 1 by a 9, but you just can't do that 1. You have to do the entire row. Are you with me? So I'm going to take that second row and I'm going to multiply by a positive 9. And after I do that, I'm going to add it to the first row, and your result will go into which row? The first row, because that's where you're trying to get a 0. Got it? Okay, so I'm ready to write the first row. Is it going to change? Yes, because whoops. See, this is why I need you guys doing this with me. This is supposed to be the first row. I know some of you caught that and you're saying, hey, that's a row 1. Yes, it is a row 1. Thank you. So your row 1 is going to change, which means I've got some work to do. So I am going to take 9 times the second row and then add it to the first row. So 9 times the second row will give me a 0, a 9, a 0, and an 18. I'm not doing anything to the first row, so it's not changing. And when I add them, I get a -4, a 0, a -1, and another -1. Cool? Okay. So my first row, -4, 0, -1, and -1. Row 2, am I trying to get a number in the second row to be a 0? No, I'm not, so I'm just going to rewrite row 2. Row 3, am I trying to get a number to be a 0? Yeah, I'm trying to get this -9 to be a 0. So what do you think you're going to do to make that happen? Good. You're going to take 9 times the second row, because I need that 1 to be a 9, add it to the third row, and the answer goes in the third row, because that's where you're trying to get a 0. With me? Okay. So let's see the work we have to do. So 9 times the second row, and then add it to the third row. So 9 times the second row is 0, 9, 0, and 18. The third row is 0, -9, -1, -19, which gives me 0 and 0, -1 and -1. Okay, 0, 0, -1 and -1. Good? Cool. So help me out. What did we just do in this particular matrix? Yeah, in this particular matrix, we eliminated the y's, didn't we? Can I reduce any of the rows? No, I can't. Okay. So now that we've eliminated the y's, what are we going to do next? You're right, eliminate the z's. So hang in there, I'll be right back and show us how to eliminate. Okay, so we just eliminated the y's, now it's time to eliminate the z's. So if I look at my rows, I have nothing to reduce. So in this case, I'm going straight from eliminating the y's to eliminating the z's. But again, as we've done before, you should identify the main diagonal. And now you're looking to eliminate the numbers above and below, and we're looking to eliminate the z's in this case. And the only number I'm allowed to use to help me get rid of those z's is that number on the main diagonal. Because I'm not making that a 0. Not on purpose anyway. Cool? Okay, so in this case I only have one z to eliminate, and that's that -1. So, here's the deal. And the choice is yours. You can either multiply the first row by a -1 or the last row by a -1, the third row. It really doesn't matter which one you multiply by a -1, you'll get the same answers. So I'm going to multiply the first row by a -1. I'm going to add it to the third row, and my answer is going to go in the first row. Does that make sense? Okay. Now, since I'm trying to get a 0 in that first row, I've got this work to do, don't I? So let's come off to the side and do that work. So -1 times the first row, which would be 4, 0, 1, and 1. Add it to the third row, 0, 0, -1, and -1. And I end up with 4, 0, 0, and 0. Well, so be it. So there's my first row. 4, 0, 0, and 0. The z in the second row is already a 0, so I'm not going to do anything there. Okay? And then I'm not trying to get a 0 in that last row for z. Okay. So now, Gauss-Jordan says get zeros above and below the main diagonal. Done. They also say as the very last step to make sure the main diagonal has nothing but positive 1s on it. So, I need to make that 4 into a positive 1. I need to make that negative 1 into a positive 1. So here's the deal. How do I make a 4 into a 1? Yeah, you don't minus by 3. You can, but trust me, no. Yeah, you divide by 4. That's the simplest way, right? Okay. So, again, this one eliminated z. And now we are going to take the first row and divide by 4 in order for us to get a 1 on that diagonal. So that's going to be 1, 0, 0, and 0. Okay, no fractions. Yay! That second number in the diagonal is already a positive 1, so I can leave the second row alone. The third row, that number is a negative 1, so I'm going to take the third row and divide by a negative 1, which will give me 0, 0, 1, and 1. Okay, so in this particular matrix, we made the main diagonal equal 1. That's what we did. Cool? All right, so now it's time to reinterpret this matrix and what it's telling me. Remember, the first the first column are the x's, second column are the y's, third column are z's. This represents an equal to sign, and that represents your answers, doesn't it? And each row is an equation, isn't it? So if I look at the first row, I've got 1x, 0 y's, 0 z's equals 0, which basically tells me x equals 0, doesn't it? Good. Let's look at the second row. The second row says 0x plus 1y plus 0z equals 2, which means I have y equals 2. Yes? And the last row says 0x plus 0y plus 1z equals 1, which means z equals 1. Good? So, you have an ordered triple. 0, 2, and 1. X, y, and z. That's your ordered triple. So if you actually graph this in 3 dimensions, which I know you won't, but think about it. You have your x-axis, your y-axis, and the z-axis is the front and back axis. Okay, that gives it the dimension, that gives it the 3-dimension look. So according to this answer, 0 for x, so don't go left or right. Go 2 up for the y's, and 1 forward on the z's. So your answer would be out in this space, the connection of those 3 lines. Good? Okay, something else I need you to remember. This is known, if you remember your elimination method or substitution method for that matter, this is known as a consistent system. A consistent system means we actually have a solution. Yes? Loving it. Hang in there. Got another example. So let's take a look at the second example. They'd like us to solve using Gauss-Jordan elimination, or, as the authors of the book call it today, row-reduced echelon form. So first off, you need to make certain all the equations are in the correct format. Are they? Yes, all the variables are on one side in alphabetical order, and the numbers are on the other. So what order matrix do you think you're going to be setting up here? Yes, you will be setting up a 3x4. 3 rows and 4 columns. By the way, if they tell you to use matrices or Gauss-Jordan elimination or row reduced echelon form on a system of equations with two equations and two unknowns, I'd say don't. Because this method is too powerful for such a small system of equations. This method, Gauss-Jordan elimination, is best used for equations, system of equations, that have 3 equations and 3 unknowns or higher. Got it? Okay, so let's set up the matrix. We know it's going to have 3 rows and 4 columns. So my first row is going to look like this. My second row, and lastly my third row. Got it. Now, what do we do next? Yes, we identify the main diagonal. And what's your goal? Your goal is to get every number above and below to be a 0. Excellent. Starting with which ones? Good, starting with your x's, which means that 4 and that 3 need to be a 0. And the only other number that you can use to make that 4 or that 3 a 0 is, yes, this 1, because this 1 is also an x and it's on the main diagonal and you're not trying to get rid of it. Got it? Okay, so let's talk about how we're going to do it. Yes, we are going to take that first row. Remember, you need that 1 and that 4 to be the same number because I'm getting rid of the 4 first. Good, so take the first row and multiply by a -4. Add it to the second row and your answer will be in the second row. Good. Okay. So, my first row, am I trying to get a 0? No. So I'm just going to rewrite the first row. Your second row, are you trying to get a 0? Yes, and this is the work you said you had to do in order to do that. So, we're going to do -4 times the first row, which will give me -4, 12, -16, and 44. And row 2, you said add it to row 2. So row 2 is a 4, a 1, a -1, and a 0. So looks like my second row has some very interesting numbers. Huh. Well, so be it. So my second row is 0, 13, -17, and 44. Got it. Just got rid of that 4. Now it's time to get rid of the 3. Okay, by using the 1 because it's on the diagonal and it's also an x. So what are we going to do? I need that 1 and that 3 to look alike. What do we do? Good. You take the first row, multiply by -3, add it to the third row, and the answer goes into the third row. So you said take -3 times the first row. Well, that looks like -3, 9, -12, and 33. And you said add it to that third row. 0, 13, -18, and 42. Well, these numbers are just as lovely as the other ones, aren't they? 0, 13, -18, and 42. So what did we just do from the original matrix to this one? Yes, we eliminated x. Now take a look at this matrix. Is there any reducing that we can do? Can I reduce any row? Nope, I can't. So I'm going straight from eliminating x to eliminating the y's. With me? Okay, be right back to eliminate those y's. Okay, so we just got rid of the x's. Time to get rid of the y's because we decided there was no reducing that we could do of any of these rows. So, first things first, that's right. Identify the main diagonal before you get rid of those y's so you can see. Most of us are visual people, so identifying it visually is actually really helpful. So I need to get rid of the -3 and the 13, correct? Okay, so let's look. The 3 is going to go first, which means I need to make that -3 and this 13 on the main diagonal the exact same number. What number can I make them into? Yep, a 39. Boy, this isn't looking very good, but so be it. So, what do you got to do to the first row? Yes, you're going to have to take the first row and multiply by 13. And you're going to have to multiply 3 to the second row. And the answer is going to go in the first row. So, I want to write my new matrix. But I got some work to do. So you said take 13 times the first row. So that would be 13, negative 39, 52, and negative 143. And then we said add it to 3 times the second row. So 3 times the second row would give me 0 and then 39, negative 51, and 132. And when I add these, looks like I get these numbers, which look a lot better than, well, look a little bit better, don't they? Okay, so my first row has now been turned into a 13, a 0, a 1, and a negative 11. So second row, am I trying to get a 0? No, because that's the number on the diagonal. So I'm not trying to make the number on the diagonal a 0. So I'm going to write down that second row. Third row, am I trying to get a 0 in the third row? I certainly am. So I'm getting rid of this 13 using that 13 on the main diagonal. Yeah, one of them needs to get multiplied by a negative 1, and it really doesn't matter which one you do, you'll get the same answer. So let's take, let's take negative 1 times the third row. Add it to the second row, and your answer goes in the third row. Okay, so we said take negative 1 times the third row. Well, that'll look like 0, negative 13, positive 18, and negative 42. Add it to the second row, which will be 0, 13, negative 17, and 44. And when you add them, we get, oh, that doesn't look too bad, does it? Okay, 0, 0, 1, and 2. All right, so what did we just do from this matrix to this one? Good, we eliminated the y's. Can I do any reducing of any rows? Nope, so now what are we doing? Time to eliminate the z's. So I'm going to erase this information down here to give me, or this work I should say, I call it my side work, to give me a little bit more room because we actually have room to eliminate the z's right now, so this is a good thing. Okay, so what are you going to do first? Yes, you're going to identify the main diagonal. And what numbers are on that main diagonal? That's right, 13, 13, and 1. And what numbers are you trying to get to be a 0? Yeah, the z's. So you need that 1 and that negative 17 to be a 0, don't you? Does it matter which one? No, it doesn't matter which one you make to be a 0 right now. Or, pardon me. It does matter which number you get to be a 0 first. Keep things in order, top to bottom. That 1 needs to be a 0. Okay, so one of these needs to get multiplied by a negative, doesn't it? Does it matter which one? Nope. So I'm going to multiply the third row by a negative 1. Add it to the first row, and my answer goes in the first row. Okay. So we said take the third row and multiply by a negative 1. So that will look like 0, 0, negative 1, and negative 2. We said add it to the first row, which has the numbers 13, 0, 1, and negative 11. And when you add them, this is my new first row. 13, 0, 0, and 13. Okay. Am I trying to get the number in the second row to be a 0 for the z's? Yes, I am. That negative 17 needs to be a 0. but I can only use that one, which means what are we going to do? Yes, we are going to take that third row and multiply by a positive 17, right? Because I need those numbers the same, but opposite signs. And then we'll add it to the second row, and the answer goes in the second row position. Okay, so we have to do 17 times the third row, right? Which will give us 0, 0, 17, and 34. And then we just have to add it to the second row, which is 0, 13, negative 17, and 44. 0, 13, 0, and 78. So that looks like our new, whoops, I'm sorry, I forgot to say plus row 2 here. So that looks like our new second row. So 0, 13, 0, and 78. And then, yeah, the third row, we just copy it back down because we're not trying to get a 0 in it. How are we doing? So far, so good? Okay, so remember, this matrix eliminated what? Yeah, it eliminated your z's. And now this last matrix, yeah, you need to get the main diagonal to all be 1s. So I got to take the first row and divide by 13, and I have to take the second row and divide by 13. And when we do that, 1, 0, 0, 1. 0, 1, 0, and, yeah, 78 divided by 13 is 6. Because you said take the second row and divide by 13, didn't we? And the last row, okay, how's that look? Good. So got an idea? Yeah, according to the first row, x equals 1. According to the second row, y equals 6. And the third row, z equals 2. Remember, this matrix, this last matrix, was getting your main diagonal to equal 1. Correct? So, your final answers, or your final answer is 1, 6, 2. That's your ordered triple. It is still a consistent system because I have a solution. Got it? Okay, got a third example for us, so hang